Yes.
So before starting, let me give you some basic recap. So yesterday we have studied about the different types, the applications, and what type of questions can come. Even for the classifications of the aircrafts, we have seen that different types of questions can come, and what are the different types of classifications that we talk about. Then flight vehicle parts we have seen, then we have seen that how this part vehicles are, what are the important control moments also we have seen, and what is a fundamental reason of making that deflections or the motions, the rolling, pitching and yaw motion. We have seen that in the last class. In addition, we have also discussed the different types of wing configuration, and each of this wing configuration, what are the certain applications, certain advantages and disadvantages. We have, I think, discussed that. So application based questions we have gone through, different type of delta wing we have discussed, and we have also discussed different type of platform where we can use that, which type of wing, which type of aircraft is going to be suitable. We have also discussed some basic layouts of the propulsion system, how they difference from air breathing and non-air breathing, what are the different types of engines are there, and each of these engines also fly at certain speed range. So we have spoke about the fuselage yesterday, how the fuselage pattern get differ from aircraft to aircraft, depending on the small aircraft, the glider. The first one is the glider, the second one is the small aircraft, the third one is for the fighter, and the last one is for the transport jet. So these are the basic layouts of the different types of fuselage pattern. Then we have also discussed the application as well as the different types of your tail plane that we have, it exists. Okay, now can you remember what is the B, the B option is there, right? So what is the name of that? What is the name of that?
Cruciform.
Very good, the name is cruciform. And here we have D type. Can you tell me the application of D type?
UAVs.
Sorry.
UAV
Yes, very good.
in
So it will be
UAVs.
there for the UAV. So all these basic applications we have discussed. Now I would like to also highlight one more important factor, that why they prefer to use this V shape. Mostly it is not for all UAV, but majority I can say they prefer to use V shape. Especially USF UAV, if you see that those are of this V shape. This kind of whatever the design configuration they make a layout. So if they use the V shape, it provides better stability. So that's the main reason they use this V shaped. Okay.
Please, ma'am, H and I type, ma'am, please difference.
I type. I is an inverted type. The D
Inverted
and
type.
I. Now see, this is an inverted V. I is an inverted V. Now see, these are very not widely seen. So there are some aircrafts which are been purposely proposed for the research activity, some kind of survey, or basically found in, even some are, some aircrafts are there like a submarine breast. So they even prefer to use this kind of mechanism. And if you see if some Russian aircraft, fighter aircraft, they have this kind of inverted type. So not all, not we cannot see so frequent, so widely, but very few of them have this configuration. These are not well popular as this group. Okay, now based on your design, you may fit that which is going to be the suitable one for you. That is completely up to the designer. Okay, and G and H are, G is an Y type configuration and H is an inverted Y configuration. Again, this type of are like, these are for the research is going on this. Very few aircrafts they have experimental purpose, they have made this type of configuration. Okay, but not widely used.
Advantages of A to H type. What is the difference advantage of A and H type?
A,
A and H type. And what is the difference and what is the advantage for this type in inverted wing, inverted tail?
you're asking the difference of an inverted tail?
Yes, ma'am.
Okay, so you can see inverted tail, it is inclined at some angle, isn't it? And here you see the, first of all, in A is a conventional one. Okay, here A is an conventional one, and whereas in the D it is an V-shaped tail plane, and this E1 is H tail plane. Now this type of configurations, if you see, you can see for the smaller aircraft. Okay, and mostly this conventional pattern are widely used for large, like cargo pattern. Even cargo, it depends on lot many factors. Now I would like to give a unique difference between A and C. C is a T-tail configuration. Okay, T-tail plane configuration. Now as I've said, the T-plane are mostly used in business jet. Business jet. Now business jet, when we talk about, like for a very lightweight business jet, okay, or a medium range business jet. So in this kind of business jet, what happens, the wing configuration and the tail are the lever arm. Okay, the movement lever arm. So I know what is mean by lever arm. We represent as LT. Do you know that lever arm? If you don't know, please tell me. What is lever arm? My dear students, do you know what is lever arm?
No, ma'am.
Okay. So do you know the nomenclature of aircrafts? What are the different factors we have?
Nomenclature, I think we know that.
Okay. So fine. Do you know what is
Is the pylon and lever arm is same?
no. Pylon is different. Pylon is this one. This is the
Yeah.
pylon. So how these engines are attached with the wing structure, that is pylon. Okay, and lever arm is a distance from the center, you can say mean aerodynamic chord, okay, to the mean aerodynamic chord of a wing to mean aerodynamic chord of an your this horizontal tail, whatever, it's a horizontal tail or vertical tail. So two types of movement lever arm. One is a fin lever arm and second one is a tail lever arm. So if we have a horizontal tail, so define as a tail movement lever arm or tail lever arm. And if we have a vertical tail, if you are measuring the distance, so that is called as a fin lever arm or vertical tail fin movement lever arm. Anything you can say.
Can you show in the diagram? Can you show in diagram? Like
Show in the,
diagram figure.
just a second. Can you see the slide right now?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So I hope I made it clear. So for the distance between the quarter chord of the wing to the quarter chord of the your horizontal tail or stabilizer, you can say. Okay. So similarly, this is for the tail lever arm. So this is a very important parameter to decide the stability factor. Second important factor of this, it decides that whether when this aircraft, just imagine this is an aircraft, and when the flow is moving over the wing, and what is the vortices, and this vortices are giving any interference to this horizontal stabilizer or the vertical stabilizer. Okay, so this creates an interference if both lie on the same plane. I hope you know what is FRL. What is FRL? Fuselage reference line. So that is one of the you can say imaginary line. So whether the wing will be fixed on the fuselage reference line or below or above. Okay, so these factors you should know before starting. So what happens in a business jet? The distance of this tail lever arm is very short. So for that reason, so there are a lot many vortices that interrupts the flow over the horizontal plane. So that creates an instability to the aircraft. So that's why we prefer to use T-tail configuration for a business jet. Alright. So I hope you know, now you know with a nomenclature. So let me revise the nomenclature once again before going into the core. Kindly mute yourself. If I'm asking anything, you can unmute and speak. Okay. Now, first and foremost is a aspect ratio. Then we have taper ratio. Then we have mean aerodynamic chord. We have sweep angle. We have twist angle. Okay. Twist angle of two types: geometric twist and aerodynamic twist. Okay, then obviously airfoil part. We have lever arm, okay, fineness ratio, okay, tail lever arm. Okay, so I think I have done right. So these are the basic nomenclature. So what is aspect ratio? Anyone? What is aspect ratio?
B square by S.
Wingspan by area, ma'am.
B square by S. What is S? Is a
Area of the plane form, ma'am.
yes, and the B is span.
Of
That
the
means
span, ma'am.
from one tip to another tip. Okay. Now you tell me what is the difference with the weighted wing area and this is called as a wing reference area. Okay, this is actually the wing reference area. So how these two are different, the weighted wing and this reference wing, are they same?
Ma'am, wet wing is what with the air, ma'am.
Sorry,
Here what is attached with the wing with the wetted wing.
any other answer? What is weighted and what is reference? Very simple. See, this is a wing structure. What I have said here, I have calculated from the distance from here to the other end, one tip to other tip, what is the area. This weighted area refers that is the area which is submerged under the fluid. That means some part of the air, that is how much portion of the air is touching the surface. Okay, touching the surface. So it is flowing over here. Some part is hidden inside the fuselage. Okay, so that may be not be taken in the account. So how much area is submerged into the fluid or the air? So that is meant by the weighted area, and reference area is without considering anything. Likewise, the total consideration is called as a reference area. Now this is talking about application. You should know which aircrafts, what is the range of their aspect ratio. Okay, now I will categorize you in some 4 to 5 different applications. First I will start with a glider or sailplane. Then I will discuss about some transport in general. Okay, transport or civil aircraft or cargo aircraft. Then I will discuss about some fighter aircraft. Then we'll discuss some more missiles. Okay, alright. Now you should know some ranges of the aspect ratio. So talking about the missiles, so it should be ranging from 0.3 to 1 aspect ratio. Fighter should range from 1 to less than 4 or sometimes 6. Okay, so military and the fighter all within that 1 to 6. Okay, and transport, it starts from 6 to 12. For glider, it starts from 20 to 35. So these are the basic range of aspect ratio. I hope you are noting down these points. Then comes to the very important factor is a taper ratio. Taper ratio, what is taper ratio? It's mathematically termed as lambda Ct by Cr.
Root chord upon tip chord upon root chord.
Very good. Tip chord upon root chord. Okay, so for a rectangular wing, if you have a rectangular wing, what will be the aspect ratio? Sorry, what will be the taper ratio?
1, ma'am.
Very good. It has to be 1 because both in the tip and both in the root are same. So it will get a 1. So in exam you will get such kind of thing. So what will be the taper ratio of a of a rectangular, or they might give you. So if the tip chord is 1 meter, what will be the root chord for a rectangular wing? So you have to, both are same. So the answer is going to be the 1. Now similarly, what if there is a triangular wing, or you can say a semi-span delta wing? So root chord is given as 6 meter. What is the taper ratio? What is the taper ratio?
One by 6.
1 by 6. Did I give anything here 1? There is no value of 1, right? So it is completely touching the corner. So basically for this, that there is no distance. So that means the tip chord is 0. So 0 by 6 you will get as
0.
0. So for the triangular wing, the taper ratio is 0. But in case you have crop delta wing, you just a second. In case you have a crop delta wing, they have given CT value is 2.5 meter and CR they have given as 8 meter. Then can you find out the taper ratio? So 2.5 by 8. One more.
1.3.
Yes, comes a 0.3. So remember one more thing, always a taper ratio ranges between 0 to 1. Okay, it can be any value which tends to 0 to 1. Now talking about a very significant factors about taper ratio for a fighter. So fighter always it has to be less than 0.3 for fighter aircraft. Fighter in the sense for high speed aircraft, supersonic speed has to be less than 3, and if is for transport aircraft or cargo aircraft should range from 0.3 to 0.6. 0.3 to 0.6. Now why we need to use at some kind of taper ratio? It is to delay the stalling propagation. It is to delay the stalling propagation. So I hope you know what is stalling propagation. What is stalling? What is stalling?
When the lift becomes when the lift becomes 0.
Lift becomes 0. This is a stalling. So if you are going for an
When the angle
interview,
reach critical angle, ma'am.
sorry,
Like,
can
yeah.
you repeat once again?
Angle reached critical angle means then the flow separation
So what
occurs,
do you
no?
mean by
That is
critical
first step.
angle? What is mean by critical angle? What is that critical angle?
Maximum angle that can attain by the aeroplane.
Maximum angle of attack. So that means if this wing having one kind of control surface and if it contains up to 90 degree, so that is this is a maximum angle you are talking about.
Ma'am, critical angle is at that angle where the CL generated is highest.
That's the point. So when you're talking about the critical, you should define what is mean by the critical. Okay, so you should not see this kind of even question they will ask you in interview. So whatever you're uttering from your mouth, ensure that give the right answer. Okay, so stalling, if I have to draw it graphically, this is angle of attack and this is a CL. Now let's take an symmetric airfoil. So as I'm increasing the angle of attack, my lift is increasing, right? I have reached to a certain point of angle of attack. By further increase in angle of attack, my lift will fall drastically. My lift will fall drastically. Okay. Now there you can connect this. This is a very, as I've said, get always look for a connectivity. So here I can ask you one question, a very connectivity kind of question. What's the reason behind of falling this CL? What is the reason behind it? What is actually happening as we increase the angle of attack? Flow separation is occurring, right? Now if there is a option, certain options, and what will happen? Okay, drag increased. Okay, then due to this what will happen? Drag increased, Reynolds number increased. Okay, then you have that boundary layer separation occurs. Then we have adverse pressure gradient, okay, pressure gradient, then all of the above. What is going to be your right answer? What is going to be your right answer?
All of the above.
All of the above.
Right? So from this question you got the idea that what are the factors can happen. So if for a certain airfoil beyond the maximum the stalling angle, if I am increasing that angle of attack, what will happen? It will lead to increase drag. So obviously my lift will fall. So it will increase or generate high Reynolds number, which is not at all advisable, which will create turbulency. And due to the formation of turbulency, what will happen? The boundary layer separation will lead. So due to the boundary layer separation, it will lead to an adverse pressure gradient. Is it clear?
I have a doubt, ma'am.
Yes, please.
Velocity at stall will be minimum only, no? Because CL will be maximum of the condition.
CL is a?
See, at stalling conditions, the CL value is maximum, so the velocity at stall will be minimum only, no, ma'am.
I am talking about beyond that. If we further increase the angle, what will happen? I am not talking about this region. I am discussing about the stalling part. What are the factors will happen if we increase the angle of attack? So at this point, the CL will no longer will increase, because what will happen? So there is a lot many wake formation over the surface. So due to that, what will happen? The force, okay, the summation of the force, whatever the lift was producing, this force will be, downward force will be more dominant on that time. So due to that, the lift will get cancelled off and drastically it will fall due to this flow separation. Okay. So whatever we are discussing, please have the clarity of the things, because nobody is so sure what type of questions they will ask. So maybe some of the questions may be hidden behind this explanation. So during the final exam, you have to find out the solution for it, and similar kind of way you have to practice your preparation. Fine. Okay, now we have discussed the taper ratio. Now coming to the mean aerodynamic chord. Okay, now tell me one of the of the air wing platform where the chord and the mean aerodynamic chord is same.
Horizontal.
What is mean aerodynamic chord and the chord is?
Mean aerodynamic chord is the distance between leading edge to tailing edge.
Okay, what is chord then?
Chord in horizontal wing, there is same chord, or mean aerodynamic chord is same.
So one thing you have to understand here, what is mean aerodynamic chord? Suppose we have a taper ratio, or we have a tapered wing. Okay, for an example, it's a straight like this kind of wing. Okay, so here we have certain tip, here we have a different route. Both are not same. Okay, now here the distance is 1 meter, here the distance is 2 meter. Now you have to take the mean of the chord. So in that case, you have to find the mean aerodynamic chord. But if we have, kindly please mute yourself. Kindly, wherever it is, kindly mute. Okay. So if we have a rectangular wing, okay, so rectangular wing, both the tip and the root are same. So for this case, the question I've asked, the answer lies here. So for rectangular wing, So there won't be any difference because throughout the section the chord is same. So the mean aerodynamic chord, if you use the formula to find out the mean aerodynamic chord, it's going to be the same, because across the wing section both the tip and the root are same. So it will not affect the mean aerodynamic chord. But if you're using delta wing, if you're using swept wing, if you're using taper wing, so there will be a difference in the chord, mean aerodynamic chord with the chord. The chord definition is same. Okay, the chord definition is same. So however we take, the imaginary line joins a horizontal line that joins between the leading edge to the trailing edge. But the value of chord might be differ for the tip, for the root, and due to the difference of that we will create some mean aerodynamic chord. Okay, so that's a difference between chord and mean aerodynamic chord. So try to understand the basic which I am pushing you. Okay, then swept angle. Now swept angle, what is a swept angle? So let's imagine this line which I have drawn here, a red color line, that is a horizontal line, and this is how the free stream air is heating. Now this wing is subtended at some angle. So this inclination of angle is known as the swept wing. Okay. Now what is the benefit of swept wing? Being this swept wing, it tends to reduce the thickness to chord ratio. Now what are the factors that it affects the thickness to chord ratio? If the thickness to chord ratio decreases, the total weight of the aircraft tends to decrease. Another benefit, it can improve the speed profile, speed of the aircraft. Another benefits, it decreases the drag. Okay, so there are many things about thickness to chord ratio. Okay, so what should be the percentage of thickness to chord ratio based on the application? So for a fighter aircraft, what should be the thickness to chord ratio? If you're designing, if any designer are going for the transport or cargo aircraft, what should be the thickness? If it is a very low speed aircraft, what should be the thickness to chord ratio? So they ask application based, how the things or factors are connected with the parameters. All those things you have to be always be clear with the facts. Is it clear till now? Any doubt?
No, ma'am.
Okay, fine. Next, I will move to the twist angle. This is a very important part. Obviously, whatever we have explained here now, that is also equally important. Now, this is equally important. Why? Most of the students get confused with two types of twist angle, geometric and the aerodynamic twist. Now first, before proceeding with the twist angle, should I rub this entire screen? Have you noted down everything?
Yes, ma'am.
Fine. So it will be better. Now what I have said, geometric twist, another is the aerodynamic twist. The concepts are very simple, but it tends to make you confused. That's all. Okay. Now first I will talk about geometric. Now by the word you can understand that it is something related with the geometry. Okay, so let's assume a wing. Okay, assume a wing. So geometric means the geometry is going to be the same. Just remember that. Geometry means that which kind of airfoil. So there are many different types of airfoil. If I say NACA 2412, maybe 0009 or 23012, so there are different types of NACA geometries are there. So in the geometric twist, the geometry are going to be the same. Remember this. So what does that mean? So both in the tip section, this is a tip section and this is a root section. Both in the root section and the tip section, we are going to use the same profile. For an example, if I am using 2412 profile over here, here also I will use 2412, or across the section I am going to use the same. But what is the difference? This angle of attack or this angle of attack may differ. If this angle of attack is 0 degree, here I might increase or decrease some plus and minus 1 degree. So this defines a geometric twist. Did I made you clear? If not, please tell me, I will
Yes.
repeat. If I have not made you clear to some fellows, I will repeat once again. Geometric twist means, see, the word geometry means something related with the profile, airfoil profile. Here we are going to use the same geometry. Remember this alone. We are going to use same geometry. Okay. Now both the root and the tip section we are using same airfoil configuration, but the angle of incidence or angle of attack going to be the different. So it can be if for an example here we have a 0 degree, here it can be plus and minus of 1 degree. Okay, so this defines the geometric twist. Now coming to the aerodynamic twist. Okay, so as here we are using the same, obviously the other one is not going to be the same. Not the same. Remember that. Remember this alone and understand what I am saying. So what we are going to do? So not same means, it means that both in the root and the tip we are going to use a different types of airfoil. So if I am the root section, I am using NACA 23012, 5 digit, and with the same incidence I am using here NACA 0009, symmetrical airfoil I am using. So due to the difference of the tip section and the root section, it will generate some twist in build. So that is known as an aerodynamic twist. So basically in aerodynamic twist, there the profile is or the geometry are not going to be the same factor. It's going to be the different. Okay, here we are using different. And geometric, we are using the same geometry but the different angle. Here we are using different geometry with same angle of attack. That's a basic difference between this geometric twist and the aerodynamic twist. Now this you can expect these questions in a different forms. Okay, so they can give you this way, that tip section this profile, this section this profile. So find out which among this profile is going to be as an aerodynamic twist. Okay, so you have to ensure about it. Done? Okay. Yes, any question?
No, ma'am.
Okay. Right. Now, before proceeding further, let's give you some basic layouts. What are the different types of loads that acts on an airplane? So, these are the 7 basic different types of loads that acts on an airplane. Okay. So, air load, inertia load, power load due to power plant, landing, takeoff, taxiing, towing, jacking, and burst truck, etc. Okay. So, what are the different types of air loads? Or they can ask in this way. Which type of loads are play a very dominant role? So the answer is going to be the air loads. And second most, due to the air loads, it helps to initiate a inertia load. Now obviously by the word called as inertia, it is clear to you. This inertia load creates because of the motion of your aircraft, or as it is flying at some medium. Okay. So this is in general layouts. So they can ask you now. They can also ask you some basic about the structures. Like we know that what are the general structures of our aircraft, internal structures, ribs, spars, stringers. So I'm not giving you all those things because already you know. But here what I will discuss is the application. Okay. So there are certain aircraft they use multi-rib wings. So where this multi-rib wings are used in the transport type. Multi-spar used for the high speed or the fighter. Now instead of fighter they can also ask you that supersonic aircraft, supersonic passenger based aircraft. So which will also comes under multi-spar wing. Then single spar. So single spar wing is going to used to get configured for an sailplane. Now there are some UAVs or some high endurance, high altitude long endurance. So they use a typical type of profile, tubular spar wing. So they use this configuration. So these are the basic layouts. You can take a screenshot or you can note down this important configuration. Right. Now coming to the very important part. Last class we have discussed about atmosphere. Now to understand this atmosphere, how this things occurs, what are the layers already I have discussed. Now today we are going to discuss a very important topic called pressure altitude, density altitude, and some of the different air speeds, okay, that influence the aircraft. Now before that I would like to give you a general outline about ISA before starting this pressure altitude and the density altitude. What is ISA? What is ISA?
International Standard Atmosphere.
Very good. It is an international standard atmosphere. What it does? What is the purpose of this international standard atmosphere?
Because when different places have different atmosphere and different altitude, so internationally we selected a one value for all of all of country, because different country has a different altitude, pressure, density, etc., etc. But internationally there is one value for all the countries.
Right. So obviously, so you do agree. So as we have different stages of our layers like troposphere, stratosphere, mesosphere. So each are have different timelines, you can say timelines with your altitude, different altitude range. Okay. So this range, when any and the molecules are also be varying. Some part is a homosphere, some part is a heterosphere, right? Now there are several factors that gives a huge variation and dependent factors. So first is a temperature, density, pressure, and the velocity. Okay, so these are the very important factors which either affects the performance of the aircraft, or it helps to affects the performance of the engine, and also affects some of the aerodynamical profile of the aircraft. Okay, so this is very important to understand. Now, why we have this ISA? As you know, some different as a Earth, I said why we have a different ranges at different places, because there's a sun here, it's directly hitting the earth's surface, and it is very narrow if I look to the polar region. So here the heating is very narrow, and here the heating is very concentrated. The heating is obviously concentrated, and if the heating is concentrated, you know from a basic principle, if the heating on the surface, what will happen? So definitely the air molecules, the surface will get warm up, so the molecules will get randomized and will move upward, and it will execute till the layer of your the troposphere. Beyond that it cannot escape back, so it will go back, diffuse it, and move to the other region, and it will reach to the pole. And when it reaches to the pole, this condensed air, the warm air, get cools down, and it condenses down to the polar region. And as in the polar region, the heating of the surface is very narrow, very low. Okay, very low, and here the heating of the surface is very high. So what will happen to the density? Density will start to flow likewise. Okay, so here as it is having a low temperature, so density will be high, and as it is a warm temperature, so the density will be low here. The temperature high, so density will be low. Could you follow? Now, so if from the high to low, it will start to move. So this is actually how a circulation process works in any atmosphere. And due to this region uneven heating over the earth's surface, so the pressure profile, pressure, density, temperature, all those profiles again creates a huge impact on the atmosphere. So when the pilots are flying at certain altitude, so they need to follow some standard pattern for it. Okay, they need to follow some standard value for calculating to understand at what altitude they are flying. Okay, so what altitude they are flying. So there are several instruments to find out the correct value. So this ISA parameters help to find out the correct reading or correct location, okay, or correct speed. Now how they influences? Now first and foremost, as we increase the height, okay, from the earth's surface, as we increase the height, how it affects with the pressure. First we'll discuss with the pressure. What happens with the pressure? What happens with the pressure? Decreases or increases? At high altitude, what happens with the pressure?
Decreases.
At high altitude, the pressure decreases.
The pressure decreases. What happens with the density?
Density
Also, ma'am, decreases.
also decreases.
Decreases, ma'am.
Density decreases. What happens with the temperature?
Temperature, ma'am.
Temperature is also-
Increasing at stratosphere and
Temperature
then
has a different case.
same
Like,
troposphere.
after
Depend
troposphere,
upon-
it's constant.
Yeah.
Okay. So
After troposphere, like it's constant for some time. Like it is different on different altitude.
right. So if I look to the troposphere, so troposphere, what happens gradually as we increase in temperature, as we increase in altitude, the temperature falls. Okay, so near to the troposphere, what we say, it is almost stratosphere, so it is almost constant, right? The temperature is almost constant from 11 kilometer to approximately 20 kilometer, it get constant. Now after a certain point, again what happens in the troposphere, it started to increase. Okay, so the graph is something like this. Just a second. I think if I draw the graph, okay. Okay, so if I draw a graph, this is a temperature variation and this is a altitude variations for an example. Okay, so at sea level, what is our standard temperature we take 15 degrees Celsius, isn't it? So from 15 degrees Celsius, let's take an assumption of approximately 11 kilometer. What happens at some point it started to decrease. That means as I'm increasing the altitude, my temperature falls. Now in between this 11 to 20 kilometer, we have some constant temperature. Okay, now 20 to 50, suppose if you are dealing with, so again it increases at certain, but if which is not as close with the 15 degree. Okay, so it is near about minus 40. It ranges from minus 60 degrees Celsius to minus 40 degrees Celsius. Okay, for an example, don't, this is a rough estimation I'm giving. Now after that, once it reaches to the layer of mesosphere, so drastically again it changes to minus 100 degree Celsius. So that's why we call as it's a most coldest region. Okay, and once it completes this mesosphere and reaches the thermosphere, and that's a point where the temperature rises rapidly. Okay, so this is just a phenomena, you have to remember it. Now two things you have to remember here: the two types of gradients, two types of regions. One is isothermal region, so where the temperature is constant. This is a zone of isothermal region. And another one is the gradient region. That means this part is a gradient, again this part is a gradient. What is meant by gradient? When there is a change in temperature with respect to change in altitude. Okay, and this is what we can identify with one word called lapse rate. Okay, so lapse rate is nothing but the change in temperature with respect to change in altitude. So what is a lapse rate? You should know the lapse rate of this troposphere.
minus 6.5 Kelvin per kilometer.
Kelvin per kilometer. Right, very good. Now there I have seen some previous year question. They have asked what is a lapse rate for a troposphere. So you should remember this value. Now sometimes they always make you twist, as I've said, that is a regular you can say like regular trends to make you confuse. So what they do, sometimes they change into from kilometer to meter, sometimes they change to degree Celsius, same value, they will keep the same value but change the unit. Okay, likewise they will change the unit to make you confuse. Okay, by meter and minus 6.5 kilometer by meter. Obviously, isn't it confusing? So when you see all those things all together, so you have to be strict with your knowledge and stick with your concept. That means in per kilometer, what does this mean? What actually this lapse rate says? That means if I take a small fragment of 1 kilometer, that means for this 1 kilometer, what is a change in temperature? Right? What is a change in temperature? That means if I draw a graph over here, if I take This is 1 kilometer. That means this change is around decreasing, the temperature decreasing about 0.65 Kelvin. That is the meaning of this lapse rate. Now, there are two types of lapse rate. One is adiabatic lapse rate, one is the environmental lapse rate. So they might not ask more detail about this environmental and adiabatic, but in case they try to confuse it, okay, so remember here we are dealing with environmental lapse rate. Keep that in mind in case they confuse you. Okay, so ensure about it. Okay, fine. Now we'll discuss some of the formulas, okay, that you have to remember. Some of the formulas for isothermal and gradient. So as the isothermal, the temperature is constant. So how this pressure and factors are different with each other. This is a formula. Okay, another one for the gradient we have T1 minus T by H minus H1. Alpha represent as a lapse rate. So there is a two formulas there, P by P1, T by T1 power G naught by alpha R rho by rho 1 equals to T by okay. This is the formula for temperature. Note down this formula. Have you noted down this formula? Now as we are talking, okay, now another thing, as we are talking about this altitude, now there are another very significant three different types of altitude. Do you remember them?
Yes, ma'am. Pressure, altitude.
So for flight testing, some different
yes,
types
ma'am,
of
yes, ma'am. Geometrical altitude, absolute altitude, and geopotential altitude.
Absolute altitude, geometric altitude, and geopotential altitude. Okay. Now what are this difference?
Absolute altitude is altitude from center of the earth.
Very good.
And
So if absolutely, if there is a flight over here, so this flight reading will be considered referring from the center of the earth. So if the earth radius is, let's consider r, and this is the height h. Okay, so that is the combination of all is the absolute altitude. Okay, now what is geometric altitude?
It is from mean sea level.
It's
Distance
from,
between.
very good, it's from the sea level. Okay, sea level. For this, suppose this is the earth surface or the sea level, so that is referred as a geometric altitude. Now why we use a mean sea level? Because if there are some terrain based airports, okay, for an example, if you look for a Nepal airports are some high altitude. Okay, so what we take as a reference as a sea level, which may differ. So based on the different terrain to terrain, it will differ, right? So that's why we take as a geometric mean sea level. Okay, so this is actually geometric altitude, that is hg. So mathematically we can write h a equals to hg plus r. Now very differently, what is geopotential altitude?
In which g is equal to g naught is equal to constant.
Sorry,
Ma'am, formula is hg is equal to hg bracket में r plus r upon hg.
what does that mean? What does that mean?
Ma'am, there is a constant gravitation. G is equal to g naught is equal to constant.
Actually, what happens, as I've said, it will vary from terrain to terrain, and this is a geopotential altitude which relates with there is some variations in altitude measurements. It may differ from latitudes, it may different from at what altitude, right? So because of the variation, what is the altitude? Suppose it is now finding in some coordinate called 88 degree north. Okay, now at some point it is flying at some 90 degree north, for an example, near to the North Pole. So there will be variations in the latitude. So variation in the latitude, how we can measure the height of the object flying. So that is defined by the geopotential altitude. So as you said, there is a formula called, this is defined as a h, which is found by r plus h suffix g into hg. Fine, clear? Now we will move to this part. Okay, it's pressure altitude. Okay. So what actually the pressure altitude? So first we'll read the definition, and okay, I hope you are all aware of what is pressure altitude. Can you tell me now? See, read this word. In other words, the pressure altitude is the altitude at airplane would be at if it was a standard day. What does it mean? Can you explain?
Ma'am, it is a pressure. Ma'am, check the pressure at a ISA and then give the altitude
Very
according to
good.
the pressure.
Very good. Very good. So for an example, in your some reading you got some value like 6 into 10 power 4 Pascal. You got some value roughly around 6 into 10 power 4 Pascal. Now you need to check, that means if this much amount of pressure is there as per the international standard atmosphere data chart, that means at what position is and at what height that aircraft is going through, okay, or flying or situated at. So that is known, suppose for 6 into 10 power 4 Pascal, as per the data it is showing it is in flying at 4 kilometer. So that means this is the pressure altitude. This is simple definition of pressure altitude actually. And similarly the same as goes for the density altitude. Suppose you have some density value, so from the density you can calculate that in the international standard atmosphere, so at what height you are flying. For example, you have 0.8 kg per meter cube you are flying. You have checked the density, it is this much. So from using this density you can able to predict what is your altitude. Okay, so with the same 4 kilometer, this is the approximate value, so you can predict this is the height that the aircraft is flying. So the basic definition of this pressure altitude and density altitude is from the pressure, okay, calculated pressure, we can able to obtain that particular flight at it is flying at which altitude. Did I made you clear?
Yes, ma'am.
Right. Now what will happen? Now in a data chart, if you observe that they have some particular range. For an example, if you see 0, 1, 2, 3, 4, 5, likewise they have some altitude and they have some corresponding temperature, some pressure, some density they will have it. Okay, now for an example, you are flying in between the 3 to 4 kilometer. Let's assume within 3.5. Now how you will able to calculate in between that? Let's make it in this way. So here we have some 7 into 10 power 4 pressure, and here we have 6 into 4 pressure. But you got a pressure something between 6.5. Okay, 6.5. Now with that pressure, how will you predict accurately that which altitude you are flying? Could you able to get my point? Am I
Yes, ma'am.
make you clear? So let's make in this way that what I have said, as we increase in height, the pressure also falls, right? So I can make a graph like this. So this is the pressure, this is the altitude, that is defining as a h. Now you have 2 points, that is one point is 7 point into 10 power 4, you know the corresponding height. Another one, you know some pressure, that is 6 into 10 power 4 at some height. Let's take as 4 and this is 3. Now you got some value which is 6.5 into 10 power some value, which is lying in between this. In between this, how will you calculate your value? That's a question, right? So there is a mathematical expression to find out the temperature altitude. To find out this temperature altitude, we can use, let's assume this one as a H1, this is as H2, or you can take vice versa, and corresponding to that, this is going to be the P2 and this is going to be the P1. Okay, P1. So the expression goes likewise, H1 plus H2 minus H1 into P star. P star is an unknown factor that you are going to find out, minus P1 by P2 minus P1. Okay, so you can able to find what is the unknown altitude, pressure altitude for that particular pressure. Clear? Please note down this formula. Now, as I've said, same definition goes for the density altitude. Now coming to the important part is the airspeed. Okay, airspeed. Now there are different types of airspeeds. Okay, now what is airspeed? It's the speed of an aircraft relative to air. Okay, so so there are different types of airspeeds out there. So indicated airspeed, true airspeed, calibrated airspeed, okay, equivalence airspeed. So each of these airspeeds are used for different purposes, and each of this, yes, am I audible?
Yes, ma'am.
Okay, anybody is asking any question?
Ma'am, that previous formula once again you show me, ma'am.
Okay,
That my internet break.
which one? This one?
That find out the pressure altitude, ma'am.
This is the formula. H star equals to H1 plus completely bracket H2 minus H1 P star, okay, star, P star minus P1 by P2 minus P1.
Ma'am, P star is sea level.
No, P star that is given over here, unknown. This value is given. For corresponding value, you are going to find what is the pressure altitude. This pressure is given to you. For this corresponding value, you need to find what is the pressure altitude.
In the denominator, P2 and P1 are
P2 minus P1. Okay, done?
yes, ma'am.
Okay. So now we will go for that. What are the different speeds we have? Okay, indicated airspeed, calibrated airspeed, equivalent airspeed, true airspeed. Now each of these perform a different what to say, different purposes. It serves different purposes. Okay, now we will see and here we have to understand the importance of it. Now I think in the I have given you the layout. This is a very very important topic, and definitely there will be one or the other question from this particular section. Somehow maybe they might not give you us to ask directly. You may you may require to use this concept to solve one problem. Okay, so that's why we are doing this thing for the first part. Okay, okay, okay. Now starting with that, first and foremost I will give you some basic tips that how you can remember this thing. Okay, so first of all, you know what is airspeed, and that definition you can measure, and how we use this, which instrument we use the pitot-static tube, and in the upcoming slide I will tell some of the facts about pitot-static tube as well. Now first and foremost, you should know how actually the airspeed that how it works. Okay, how this actually works. So first we have indicated airspeed. Now what is the purpose of indicated airspeed? It is written, what is read on the airspeed gauge connected to the pitot-static system. So we have one pitot-static tube. So from there whatever the readings are there, it will be read by the indicator. Now what this calibrated airspeed will do? The indicated airspeed adjusts for the pitot-static position and installation error. So if there is some type of instrumentation's error, so it will avoid or it will cut down the error and show the correct value for the corresponding value. Then we have equivalent airspeed. Okay, so what is that equivalent airspeed? The calibrated airspeed adjusts for compressibility effects. So if there any kind of compressible effects are considered, so that will be also taken into granted, and accordingly the calibrated measurements will be or the value will be shown to you or the pilot. Now what is true airspeed? True airspeed, it says that the equivalent airspeed adjusts for the air density and also for the speed throughout the air in which it is flying. Okay, so it will adjust each and every factors, and it will also adjust for the density and speed as well, and then accordingly it will be used. So what is the purpose? Actually it is all are controlling or cut down some error or some parameters to give the correct value or correct flight speed. Okay, so that is the main motto of using this indicators or this different types of airspeed. Now coming to the very significant point, how you can remember this easily. So when it comes that, obviously you should have some clue to remember, because for a airspeed we have indicated airspeed, we have calibrated, you have equivalence and true. So which comes after what? How will you remember that? And that sequence is a very important one. So here I myself has found one tricks to remember. So I remember a concept called ice tea. So obviously you know what is ice tea. Ice means obviously I don't have to explain, and iced tea. Just remember the concept iced tea. Okay. Now you know what are the different airspeed indicators we have. So we have indicated airspeed. I refers to the indicated airspeed. So if any questions comes relevant to that, you can remember this concept for while practicing, even while in your finals as well. Indicated, calibrated, E stands for equivalent airspeed, and T stands for true airspeed. Fine. So you remember this process very easily. You know what are the different types. So indicated, calibrated, equivalent, true airspeed. Now each of these indicators work for different purposes. Now what is that purpose? Now after remember this, in between whatever you have written here, okay, write down that I see ice. Write down the ice in this cross format. Now I will tell you why we are writing in the cross format and how you can remember this. Now first and foremost, whatever we have in the first and foremost, we know the purpose. What is it? The purpose is to identify how much amount of speed it is flowing. It measures the airspeed from different measuring gauge, okay, from the pitot-static tube. Now what this indicator, or I can say after it measures that value, what this indicated airspeed does. Okay, let's see here. it reads the gauge. So we know it reads the gauge. So let me write here, it reads the gauge, or measure from, it measures whatever the value it is to measure by this. Now what this calibrated does? It does, let's see what it does. Indicated airspeed adjusts for the petrostatic position and installation error. That means it is to clarify some error. So what is the error? It is to help to or installation. So whatever this measurements we are getting, okay, so what will help? This will calibrate, or this will give the data after clearing from the clearing the instrumental error and the installation error. Okay, then we have whatever the instrumental error will get clarified. Now we'll move to the equivalent airspeed. Now see what it says. It clears the compressibility effect. Okay, now so what the equivalence will cut off the compressibility effect. So here we have the instrumentation, here we have the compressibility. So after the instrumentation is get cut down, whatever the value we will get, so in that value we will use the compressibility effects. We'll cut down the compressibility effects or adjust it, and that value is nothing but the equivalence data. Okay. Now what this true airspeed? Equivalence airspeeds adjust for the air density or speed. So moreover it is changing the altitude error. Okay. So again it is covering up the altitude error. So here I will write altitude comes a density and velocity error. It is to adjust that. Now I hope this kind of patterns will help you to remember how actually this process, and easy to remember. Did you feel easy to remember this process? Am I audible?
Yes, ma'am.
Okay. So if you find some easiest way from this, obviously you will memorize. You have to memorize. Without that there is no other go. But if you remember some clue, some hints, you can avoid mistakes. So that's a reason, because you know when you are going for competitive exam, you will be undergoing lot much of stress. So you should know how you can cut down the stress. So during your preparation, if you remember this tips and tricks, so which will help you to avoid, or which will help you to reduce the stress. Okay. So stress automatically it comes when you have the exam, right? Especially when it is a competitive exam. So you have to remember this is one of the way to cut down this kind of stresses. So to avoid silly mistakes. So most of the student does silly mistake. Okay, and that's how their scores does not go reach up to that certain level they are expecting to. Okay, now clear? Now I will another very important part which I will explain here is the application and some formula and some questions that they ask from this, basic questions that they ask from here. Okay. Now what is the application of this? So as I've said, indicated is a airspeed measures from different gauges. right? So where we can use this indicated airspeed? Indicated airspeed is applicable, used, let me use a different color. It is used during takeoff, for stall, for lift, or during turn, or any kind of performance it is making. So that time indicated airspeed or measuring any kind of performance measurements, we can go for the indicated airspeed measurements.
So, ma'am, why they can't use true airspeed while takeoff and this stall?
Sorry, why they can't?
Use this true airspeed instead of using indicated airspeed.
True airspeed they use, there are certain errors, altitude errors are there, but this kind of performance, this is a very precious thing. So this true airspeed is used only during navigation. During navigation purpose only they use this. Okay.
Okay.
During navigation. Okay. And so both equivalence and this thing they use during navigation. Okay. Now there can be some questions. At what condition the calibrated airspeed may be same as a true airspeed? Now there can be a question. Calibrated airspeed, let's consider as CAS, is equal to the true airspeed.
Where is no compressible, no?
Very good.
Incompressible.
Very good. When there is a no compressibility effect. Okay. Or and that is actually they consider as a very standard case. Okay. This is very good. So you have to remember this point. If there is no compressibility effect, so that time the true airspeed is going to be the same as the calibrated airspeed. Now few more important facts. Here is the formula for relation between true airspeed and equivalent airspeed. Okay. Now according to me, I would like to refine this formula for the purpose of remembering in an easy way. So my point of writing is in this way: velocity of equivalent airspeed by velocity of true airspeed equals to root over of, rho means altitude, rho of altitude by rho of sea level. Now why I have written? Because there are lot many rho naught rho, so there is very confusing. Even when you practice, like you waste lot much of time by thinking whether it is rho naught or rho, rho naught by rho or rho by rho naught. Huge confusions, and with a simple problem you make a mistake because of this confusion. So always I want to when I was in your stage, I used to find this are very confusing part. So I have found one way to remember. So always I used to frame kind of alphabetical way. So we know both the side we have V. So in alphabetical order, E come first, then T come. So E by T. And in the same way, if I instead of this naught and this thing, so I can simply write of altitude, that is A come first and then S come first. So both the sequence are of same. I know there will be some root of and this thing, but this is a very confusing part, how they are related. So during your practice, if you follow these tricks, I am quite sure in your lifelong you will never forget this. Okay, so you may not know that which and where and which way you need to apply this formula, because these are the very basic things, so you need to require everywhere. So this is one of the tricks that I follow. So you may follow if you find it very useful. You can follow this step as well. Avoid confusion, because this row knot and row, it's very confusing part according to me. And please let me know whether the same thing for you. If it is same thing, follow this. Okay. So either of that, the formula is same. There is no changes in the formula I have made, but only the notations I have changed for my understanding. Yes, any question over here?
No, ma'am.
Right. Okay. Now we will do some numerical part. We will look into that. Okay. So this thing, static tube, is very lengthy. We'll do that. Okay. So let's do some problem. This is a very simple problem, and this is one of the previous year problem. So let's read the problem and solve it. An aircraft is cruising at true airspeed of 100 meter per second under ISA condition at an altitude at which the density of free stream is this much. What will be the equivalent airspeed? So again, it is a question of the equivalent and the true airspeed. So here you have to identify what are the given data. Okay. So true airspeed, they have given 100 meter per second, and they have given the altitude is 6 kg per meter cube. Now what will be the equivalent airspeed? Now equivalent airspeed, you have to find. Then what is the density? Density of the sea level, you have to remember 1.225 kg per meter cube. Now you can recall the same way, the way I have made you recall the formula. So V by V equals to root over by rho by rho. So VE by T, rho by A, and SL. This is a formula. So you can put that and tell me the right answer. Solve and tell me the right answer.
65.5 meter per second.
Are all are getting the same answer?
Yes, ma'am.
Okay. So this is the right answer. Okay, and this is another type of question. So we have not done the pitot static tube, so we will do that later on. Okay, we will do that later on. In the next class I will give a basic recap and of this, and then we'll move to the propulsion. Okay, so any questions, any doubt? One more important part I forgot, just to recall right now. Sometimes they give you one more term called density ratio. Okay, can you see my yeah, I got it. density ratio, which is denoted by sigma. So in some problem they will not give you what is the individual value. Okay, they will give you the density ratio. Now density ratio means it's a ratio between the altitude versus sea level. Altitude versus sea level. Okay, and it has to be less than 1. It has to be less than 1 because density at the sea level is 1.225. Okay. Any questions? Any question? I have clear with this indicated airspeed,
Yes,
formation,
ma'am.
what is the pressure, altitude, applications that we have taken care previously. Clear?